So the first thing we're going to do is take a look at a problem where we have two objects. Maybe they're people, maybe they're boxes, but one is 50 kilograms, the other is 100 kilograms, and they are separated by 2 meters. The question is going to be, what is the gravitational force between them? So to set this up, we would use the force of gravity is equal to big G m1 m2 over r squared. This problem looks basic to most of you probably, but I am going to tell you that when I have students enter this into their calculator, they usually have problems. We're dealing with numbers in scientific notation. We're dealing with squaring numbers. It's very important that you practice to make sure that you get the correct value when entering these numbers into your calculator. So the force of gravity in this case would equal 6.67 times 10 to the negative 11th times m1, which is 50, times m2, which is 100. I usually take those two items plus the 6.67 times 10 to the negative 11th, multiply them together on my calculator, get an answer. Your calculators carry numbers, but get the answer, then divide by, put the denominator in its own set of parentheses or brackets, because if you, depending on the type of calculator you have, when you, especially if the number is in scientific notation, you do 2 squared, you could get some really funky numbers here. So if you had, this was a number, we're going to deal with numbers that are much bigger. Just the Earth's radius is going to be 6.38 times 10 to the 6th, and then you square it, and if you're not careful, you're squaring the 6, you're not squaring the whole value, the 6,380,000. You're squaring the power of the 6, and so you have to be very careful when you enter your calculator. Get in a pattern, practice a couple, make sure you're getting the right answers, and then if you are, just keep following that. So we plug all that into our calculator. We end up with a gravity of, in this particular problem, 8.34 times 10 to the negative 8th, and this is newtons. So this is the force of gravity between these objects. Now, the acceleration that each one of them experiences is going to be a little bit different. Acceleration is equal to force over mass, and so the acceleration that the 50 kilogram object experiences is going to be twice that of the force that the 100 kilogram object experiences. Of course, if there's friction, then the force of gravity may not even be able to overcome that friction. So that's how you're going to solve one of those problems. So the second problem we're going to do is going to deal with gravity. We are going to do a gravity problem that relates to the gravity at the North Pocono High School. And so gravity, gravitation, the way we solve for gravity is big G, the mass of the Earth, divided by r squared. And so the altitude at the altitude, and let's talk about altitude here. So this is the Earth, and it has a specific radius, and this radius is going to be 6.37 times 10 to the 6 meters. But then on top of the Earth is going to be, on the crust of the Earth is going to be mountaintops and things like that. Altitude, the altitude is going to be how far above sea level an object is. And so the altitude of the high school is about 520 meters. Now, the distance in this r squared value is how far we are from the center of the Earth. So you would have to add these two values together. The interesting thing is when you add these together, the statistical significance of the 520 is, it means that we are only changing a number out beyond the 637 times 10 to the 6. But let's treat it as if we are actually making a very significant change, and we'll get a value here. So we have 6.37 times 10 to the 6th plus the 520, and so we end up with something like 6,370,520 meters. Now, the mass of the Earth is 5.97 times 10 to the 24th kilograms. Very large. So little g is going to equal 6.67 times 10 to the negative 11th times the mass of the Earth, which again is 5.97 times 10 to the 24th, divided by the radius squared, 6,370,520, and we need to square that value. And when we do this, guess what we get? 9.8 meters per second squared, which is exactly what we would have projected we would get. Now, if we are at sea level, we could get a gravity that is a little bit bigger. If we are at higher altitude, we get gravity that's a little bit smaller. The range of gravities on Earth range from about 9.78 meters per second squared up to about 9.82 meters per second squared. Okay, it's all 9.8, but we get close. And to be able to measure that and to be able to experience that type of a difference, that's something that we would not be able to do without very, very precise equipment. So saying 9.8 gets us a good value. If you have any questions on how to solve these, please let me know.